In an earlier lecture, we discussed Faraday's law in the context of multiple conducting loops connected together to form a coil. There's another configuration involving multiple connected loops that we call a solenoid. So here we show both a coil and a solenoid together so that we can discuss the key difference. When we have multiple loops of radius r sub c that are of the same size or larger than the length L sub c of the loops, we typically call that configuration of multiple loops a coil. When we have the case that the radius r sub s of the loops is much smaller than the total length L sub s of the set of loops, then we call that arrangement of multiple loops a solenoid. The geometry of a solenoid has an important impact on the magnetic field produced by a solenoid, so let's discuss that. Let's consider a long solenoid of which we only show a small portion of the total length. Let's consider the total length of the solenoid to be L sub s and that the solenoid has a total number of loops N sub s. Let's consider here that we will apply a current I as shown. For each loop in the solenoid, the current I is into the page at the top of each loop and out of the page at the bottom of each loop. When the current I is applied, the solenoid becomes a source of magnetic field with some special properties. Inside the solenoid, the magnetic field is constant, equal to the expression shown. The direction of the field is given by the usual right-hand rule for finding the B field in a current loop. However, here, the field is uniform, the same everywhere, and parallel to the axis of the solenoid, as long as we're not too close to the ends of the solenoid. Additionally, the B field outside of the solenoid is, to a good approximation, 0. Now, if we look at the solenoid from the end, here, the left end, like this, we would see, for this particular example, the solenoid B field uniform inside and pointed out of the page, while outside the solenoid, the magnetic field is 0. Let's do an example with a solenoid involving Faraday's law. Consider this end view of the solenoid with ns loops of radius rs and total length ls. The solenoid passes through a coil with NC loops of radius RC. The resistance of the entire coil is capital R. Additionally, we impose a current IS that is a function of time as shown with positive constants P and K. Let's find the induced current I in the coil as a function of time for t greater than 0. Here's our approach. Find the magnetic field of the solenoid, then find the magnetic flux through a single loop of the coil, then find the EMF in the coil, and finally find the induced current I. As we just discussed, inside the solenoid, in the shaded region shown here, the magnetic field is given by this expression and is uniform everywhere in the shaded region. Inserting our expression for the solenoid current I sub s, we have this result. We can use the right-hand rule for determining the magnetic field direction for a loop, and we find that inside the solenoid, the magnetic field is out of the page for this example. Let's remember that outside the solenoid, the magnetic field is 0. Now we can use our knowledge of the magnetic field to find the magnetic flux through a single loop of the coil. There are two regions to consider: the flux for that part of the coil's loop area that's shaded, that is, inside the solenoid, and that part of the coil's loop area outside the solenoid, unshaded. Because there is no B field in the unshaded area, there is no flux. So all the non-zero flux for the coil loop is happening for that part of the area in the solenoid. For the constant B field that's out of the page here, the flux is just B times the shaded area pi r sub s squared. And that works out to be this. Now we're in a position to find the EMF of the coil. That's just the number of loops of the coil, NC, times the magnitude of the flux derivative for a single coil loop. Differentiating, we obtain this result. We can now find our final result, the induced current I in the coil. That's just the EMF divided by the resistance R. And here it is. The direction of the current I in the coil is found using Lenz's law. The solenoid's B field is increasing out of the page, so by Lenz's law, the current in the coil produces a second B field that's into the page that tries to offset the flux increase out of the page from the solenoid. A coil B field into the page means the coil current must be clockwise. That's it for now. In our next lecture, we'll discuss new laws for electromagnetism, Gauss's law from electric and magnetic fields.